Alright, we're going to now go over the solutions for practice final number 2. The first problem is to calculate the average acceleration of the car during segment I, the 1 here. The acceleration is just the slope of the velocity versus time. So the rise is 30 meters per second. The run is 6 here. 30 over 6 gives 5 meters per second squared. Next question is the total distance traveled, going from 0 to 24 seconds. So that's just the area under the velocity versus time plot. So this triangle here has an area of 1/2 base height times base, so 30 times 6. The area of this rectangle here is 30 times 6. And the area of this triangle is 1/2 30 times 12. So we'll get 450 meters. Okay, next problem is how much time does it take to accelerate from standing start to 25.6 meters per second if the acceleration is constant and the car covers 225 meters during acceleration. So we have v initial, v final, we have the distance, okay, and we want to know the time. There's actually one equation that can give us the time right away. It's this one. Delta x is equal to 1/2 v initial plus v final is equal to times delta t. All right. You can do this problem in a more straightforward way with 2 steps, but if you want it in 1 step, this is the equation that gives you 1 step. You get 225 is equal to 1/2 of 0 plus 226.5 times delta t. Solving for delta t gives you 16.98 seconds. So probably most of you don't solve it this way. Probably what you do is do the problem in 2 steps. You would do, okay, you have the initial velocity 0, the final velocity 26.5, then you have v squared minus v initial squared, right? You have something like v squared minus v initial squared equal to 2a delta x, all right? You can do that, and then you can solve, then you would solve for a from that, right? And then you can figure out how much time it takes by, you can get delta t because you know a, you know the initial, the final, that'll be enough information to get delta t. So you can get it in 2 steps, rather straightforward. Let's go on. The speed indicator of the plane that took off from Detroit reads 365 kilometers per hour, and the compass indicates it's heading due east to Boston. Okay. A steady wind is blowing due north at 45.7 kilometers per hour. So we know that, okay, by the way, the airspeed indicator, this should probably be explained a little bit more carefully in the problem because not everybody would know this. They're talking about a measurement of the velocity of the plane relative to the air, so airspeed indicator. So I'm going to take positive x direction will be east, positive y direction will be north. So this will be 365 kilometers per hour, 0, because it's going due east. Now the velocity of the air will be 0, 45.7 kilometers per hour, since that's pure north. So they want to know the speed of the plane relative to the ground. So v plane will be the speed, the velocity of the plane relative to the air plus the velocity of the air. So I'm going to add these two vectors together. We get 365, 45.7. You get the speed, you get the square root of 365 squared plus 45.7 squared, and we get 368 kilometers per hour. Next problem. If the pilot wishes to fly directly to Boston, which is due east, what must the compass read? So now they really want to go due east. Okay, so we want v plane in the northern component, or the y component, to be 0. So the assumption here, probably this should be also explained, that the plane is still going to have the same speed relative to the air. It'll still be 365 kilometers per hour. Okay, but in order for v plane y component to be 0, we need, when we add these two together, we need that we need this component here to cancel out this 45.7, right? So we need this negative 45.7, so that when we add it to V air, there's nothing that would be in the y component, because we want the plane y to be equal to 0. Okay. So we need v plane relative to air comma y to be negative 45.7. So we need this component here to be 45.7, going in the negative y direction. The magnitude of the velocity of the plane relative to the air, the hypotenuse of this triangle would be 365. So in order to get this angle here, the angle below east, okay, south of east, that would be the inverse sine of, draw this little triangle, of minus 45.7 over 365, so we get negative 7.90. So that's the angle measured below east. But if we want to measure it from north, all the way like this, you just have to say it's 97.19 degrees from north, okay, because there's an extra 9 degrees here. All right, so by the way, I should mention this theta with the negative 7.19, that's the angle relative to east measured counterclockwise. Because clockwise is positive, I put the minus sign because it's going. Because counterclockwise is positive, I put the minus sign because I'm going clockwise. Okay, now we have a string, we have a ball, and we have the weight of the ball going down mg and the tension T going up, and we want to know whether T is greater than mg, less than mg, or equal to mg, or cannot tell for these various cases. So first of all, the elevator is traveling downward, and its downward velocity is decreasing as it's nears a stop at a lower floor. So it's going down, but it's getting smaller. Okay, so it's going down, but the amount of the velocity is going down and it gets smaller, so the acceleration is actually going upwards. So if the acceleration is going upwards, then in this sort of tug of war, the T has to be bigger than mg. T greater than mg. Next problem, the elevator is traveling upwards, so it's going upwards, and its upward velocity is decreasing, so the acceleration is actually going down. Okay, so acceleration is downward, so T is losing the tug of war, so mg is bigger than T. Now in the case the elevator is stationary, it remains at rest, so the acceleration is 0, then T and mg are equal in magnitude. If the elevator is traveling upward and its upward velocity is increasing, then it's going up and it gets faster. Then the acceleration is upward, so then T is greater than mg. Now the elevator is traveling upward with a constant velocity, then the acceleration is 0, then T is just equal to mg. Now the elevator is traveling downward and its downward velocity is increasing, so it's going downward and it's getting faster downwards, then the acceleration is downwards, so then T must be less than mg. Mg is bigger. Okay, next problem. A hanging mass, M1, is equal to 0.473 kilograms. It's attached to a light string that runs over a frictionless pulley to a mass M2, 1.23 kilograms. That's initially, okay, so I was pointing to the wrong one. M1 is here. It's 0.473 kilograms. And it's attached to a light string that runs over a frictionless pulley to a mass M2, that's here. That's 1.23 kilograms. That's on a frictionless ramp. The ramp has an angle of 31.1 degrees above horizontal, and the pulley is at the top of the ramp. They want to know, the acceleration of the mass, M2. So going up the ramp is considered positive. All right. So what we're going to do is we're going to take this as the snake-like direction because that's the convention that they wanted. Going up the ramp is positive, and then going down on this side. So we're going to treat both masses together as one unit. The net force in the s direction, we have the force of gravity in this direction, that's m1g, it's in the positive s direction. But then we have the force of gravity m2g. We need the component in the s direction, so this parallel component will be negative. It will be the sine of theta times m2g. So we'll have minus m2g sine of theta. So m1g is 0.473 times 9.80. Then we have minus m2, which is 1.23 times g, which is 9.80, times the sine of 31.1 degrees. So that comes out to negative 1.59 newtons. Now, then, we also have that the net force in the s direction is the sum of the masses, because we consider the masses together as one unit, times acceleration in the s direction. So this must be equal to minus 1.59. So AS is minus 1.59 divided by 0.473 plus 1.23, and that comes out to negative 0.934 meters per second squared. Next problem, we have the hand pushing on this mass A, which then in turn pushes on mass B. The mass of A is greater than mass of B. They want to know how does the magnitude of the work on A, how does the magnitude of the work that A does on B compare to the magnitude of the work that B does on A. Okay. Now the force of A on B is equal to in magnitude but opposite in direction to the force of B on A. That's Newton's third law. Okay. And so as a result, the work done by A on B is going to be equal in magnitude to the work done by B on A. Equal magnitude of work, not neither one is zero because the masses move. A pushes on B and B moves. Okay. Similarly, B pushes on A, but actually does negative work as A moves. Okay, next one. How does the magnitude of the net work on A compare to the magnitude of the net work on B? Okay, so that's the solutions written here. So the net work done is equal to the change in the kinetic energy. That's the work energy theorem. Now A and B move together. However, so the velocities will be the same, but A has more mass. Therefore, the change in the kinetic energy, delta Ka, is bigger than the change in the kinetic energy for B. So the net work done is bigger for A. Okay, next problem 15. How does the magnitude of the net work on A compare to the magnitude of the work of the hand on A? Now, so A pushes on B, and it goes in this direction. But B, oh, okay. So let me back up a second. So the hand pushes on A, it's going in this direction, okay. But B also pushes on A in this direction, right? So B is pushing in the opposite direction to the force of the hand on block A. So the work that the hand is doing is going to be canceled a little bit because B is pushing in the other direction. So the work done by hand, the work of the hand on A is bigger than the net work on A because B is sort of eating some of that up by going in the other direction, pushing in the other direction. All right, those are maybe a bit tricky, but conceptually it's something you should know. Okay, let's go on. Suppose you throw a 0.077 kilogram ball with a speed of 10.7 meters per second and at an angle of 28.9 degrees above the horizontal from a building. It's 11.3 meters high. So we have the initial position, initial height 11.3 meters. The final height is 0. Using conservation of energy, Ki plus Ui is equal to Kf plus Uf. Now we'll plug in the values. 1/2 the mass of 0.077. The initial speed is 10.7. The initial height is 11.3, so mg by 0.077 is the mass times 9.80 times 11.3. And that's equal to the kinetic energy, the final kinetic energy plus the final potential energy, but the final potential energy is 0 because Y final is 0. So the final kinetic energy is all this stuff here, which ends up being 12.9 joules. Now they want to know what is the speed when it hits the ground, so the final kinetic energy is 12.9 joules. 1/2 mv final squared is equal to 12.9. That gives us v final is 18.3 meters per second. Next problem. Two bumper cars moving on a frictionless surface collide elastically. The first bumper car is moving to the right with a speed of 18.4 meters per second, and rear ends the second bumper car, which is also moving to the right with a speed of 9 meters per second. What is the speed of the first bumper after the collision? Mass of the first bumper car is 193, and the mass of the second is 141. Okay, so this is equation, the last equation in one dimension, conservation of energy, and we also have the initial total kinetic energy is equal to the final total kinetic energy. But this total kinetic energy stuff is kind of a pain. So we will swap this for the fact that the relative velocity keeps its magnitude but flips its sign. So conservation energy is mv1. So okay, so we have the mass of the first car, 193 times the initial velocity, 18.4. That's the x component of the velocity. And the mass of the second one, 141 times the x component, which is 9.00. That must be equal to the m for 1, which is 193, times v1 x component, that will be the final velocity of bumper car 1, times the mass 141 times the final velocity of the x component of bumper car 2. But then we say the relative velocity flips sign, so we have v1x minus v2x would be minus the v1 initial, which is 18.4, minus v2 initial, which is 9.0. So simplifying this gives 9.4, and we get minus 9.4, and so v2x is equal to v1x plus 9.4. Now we go back to the equation we had up here. This guy ends up being 4,820. This guy here is 193 v1x, and we have 141 v2x. But we're going to replace v2x by v1x plus 9.4. So then we have 193 plus 141 v1x's, and then that ends up being 334 v1x. And then we have 9.4 times 141, that's 1,325. So now we can solve that this is equal to 334 v1x plus 1,325, and we get that v1x is equal to 10.46 meters per second. Okay, car speeds over the top of the hill if the radius of the curvature of the hill at the top is 22.67 meters. How fast can the car be traveling and maintain constant contact with the ground? So at the top speed, what's happening is that the net force, the normal force that the road exerts is going to be equal to 0. So it's just about to lose contact. And so now we have the force of gravity providing all the centripetal force. So mg is equal to mv squared over r. So cancel the m's, you get that v squared is equal to gr. So that'll be 9.8 times 22.67. Okay, and then we have that v is equal to the square root of that, which comes out to 14.9 meters per second. Next problem, we have the Yogi Bear or some sort of bear that walks out onto this beam. And we have the bar here, which has weight 220 newtons. It's 8 meters long, so halfway point is 4 meters. So you draw your force of gravity from that point, center of mass. We have tension going up. We have these goodies that are 77 newtons at the end of the bar. We have the bear, it's at distance x, so 770 newtons for the weight of the bear. So when the bear is at 1.2 meters, what is the tension in the blue support wire? So let's figure out the torques for all of the forces. So the 220 Newton force here is acting at a distance 4 meters from the rotation point here. And so we have 220 times 4, that's 880 Newton meters going in the clockwise direction. It's trying to rotate clockwise. And then we have the torque due to the 770 weight of the bear. So we have 770 times the distance x, which is 1.2 in this problem. So we have 924 Newton meters, which is also clockwise. And then we have the goodies, or no, we have the tension here, so it's going this way, it's kind of clockwise. And that will be t times the lever arm distance, which is 8 meters. So t times 8, kind of clockwise. And we have the goodies going down like this, so this goes clockwise. So that's 77 newtons times the lever arm distance, which is 8, which is going to give me 616 Newton meters. Now the net torque needs to be equal to 0. So this total for the counterclockwise torques is equal to the sum of the clockwise torques. So you have T8 is equal to 880 plus 924 plus 616. So then the tension must be, add these together, divide by 8, you get 302. Now, they ask when the bear is at x equals to 1.2 meters, what is the tension of the support wire? Okay, so now in this case, no, sorry, we already did this one. It's this one we're going to do. If the maximum tension that the wire can sustain is 616 newtons. What is the maximum distance x max that the bear may walk before the wire breaks? Okay, so now we keep x by itself. So now we have torque for 770 will be 770 times x rather than taking x equal to 1.2, just rewrite it as x. Now the tension, we're told T is equal to 616. Okay, so now we can go back to this equation. We have 616 times 8 equal to 880. Instead of 924, we have 770 times x plus 616. Solving for x gives x is equal to 4.46 meters. Okay, which satellite orbits with the longer period t around Earth? Assume the satellite assume that the orbits are circular and both satellites have the same mass. Okay, so G orbit is the square root of capital G capital M over R. Now the period for one orbit is 2 pi r divided by the v for the orbit. So we have the formula of 2 pi r, the circumference divided by the square root of g m over r. Now the square root in the numerator of the denominator of the denominator is the square root in the numerator. So we have 2 pi r to the 3 halves, and then divided by the square root of gm. So now if I look at this, the larger r is, the larger the period. By the way, the masses don't matter. The masses of the satellites don't matter in this problem. Next problem, a projectile is shot from the surface of the Earth by a very powerful cannon. If the projectile reaches a height of 30.7 kilometers above Earth's surface, what was the speed of the satellite when it left the cannon? So even though it's about a large distance, 30.7 kilometers is very small compared to the radius of the Earth, so we can use the surface on Earth gravitational potential energy formula, mgy. So conservation of energy Ki plus Ui is equal to Kf plus Uf. So Ui will be 0, starts from the surface. So we have 1/2 mv squared, and that's equal to the final potential energy, m times 9.80 times 30.7 times 10 to the third. So I'm converting the kilometers to meters here with the 10 to the third. Okay, this guy is UF, the gravitational potential energy on the surface of the Earth at a height of 30.7 kilometers. So now I solve for V. The m's drop out. We get 6.017 times 10 to the fifth. When I multiply 2 to 9.80 times 30.7 times 10 to the third. Taking the square root gives me 776 meters per second. Next problem. Okay, a mass of 0.04 kilograms can glide freely on an air track is attached to a spring. K is equal to 64 newton per meter and oscillates back and forth with an amplitude of 0.4 meters. So the total energy, the formula not on your equation sheet, but it's useful to have, it's 1/2 K A squared. Okay, so when we have 1/2 K 64 times 0.4 squared, and it comes to 5.12 joules. What is the kinetic energy at a distance of 0.15 from the equilibrium? Okay, so we have K plus U is equal to E total. We know E total is 5.12. U we can calculate, that's 1/2 K x squared, so 1/2 K 0.15 is the distance squared. So that comes out to, because K is equal to 64, this comes out to 0.72 joules. Now K then is equal to, so U is 0.72 joules, so K is equal to the total, which is 5.12 minus 0.72, that comes out to 4.40 joules. Okay, next problem. We have mass on a spring, and it starts from equilibrium position x equal to 0. So at t equals to 0, at x equals to 0, and the velocity is 16 meters per second to the right. Okay. All right. So now, first of all, we are told that x0 at time t equals to 0, x is equal to 0. So you can rule out the cosine functions. The cosine is not correct. And we are also told that that omega is equal to square root. Okay, so omega is the square root of k over m, right? And so omega is the square root of 64. So k is 64, so we get 64 over 0.04. Take the square root, you get 40 radians per second. Okay. Now the point is the formula for this. In order to get the velocity, I guess I didn't write this all out. If I have x is equal to a sine omega t, then if I take v, I get a omega cosine omega t. And we're told that at t equals to 0, the velocity is going to be equal to 16, so a times omega needs to be 16. Okay, so I have omega is 40. In order to get that the velocity is equal to 16, a needs to be 0.4. Okay, this guy here, 16, was too big. It needs to be 0.4. Okay. All right, next problem. When does the does the oscillator have maximum acceleration? Okay, so the maximum acceleration occurs when the spring is stretched or compressed as much as possible. And so the maximum acceleration then is when x is at its maximum or minimum, when the elongation is maximal. Okay, next problem. We have that traveling wave is propagated in a string. It's 4.67 millimeters times the sine of something times x minus something times t plus this phase constant. So this guy on front is 2 pi over lambda. Think multiplying x with 2 pi over lambda, also called k, the wave number. And so lambda is equal to 2 pi divided by 162.03, which comes out to 0.0388. Now, in order to get the minimum separation between the 2 points that are in perfect opposition in phase, phases, completely out of phase, we need then delta x min to be half a wavelength to get pi out of phase. So 1/2 wavelength is just 1/2 of 0.0388, that's 0.0194 meters. Now determine the separation delta x AB between 2 points AB. If B oscillates with a phase difference of 0.7801 radians compared to 0.8. So the phase difference is 0.781. We want to get this as a fraction of a full cycle, so divide by 2 pi, that's 0.124 cycles. And then we can convert this into a distance. So it'll be 0.124 times lambda, right? And that will give us 0.00482 meters. Okay, next question. A 2 meter long string is fixed at both ends and tightened until the wave speed is 50 meters per second. What is the frequency of the standing wave shown? So this is 1, 2, 3, 4, 5, 6 footballs. These things are footballs, I'm calling them. And so that's n equals to 6. The formula is Fn is nv over 2L. Take n equals to 6. We have 6 times 50 divided by 2L. 2 times 2. L was 2. And that comes out to 75 hertz. And now the next problem, we have these two waves moving with 1 meter per second. These triangles just move over. Okay, so this is at t equals 0. We want to know what it looks like for t equals 1 second. So each triangle moves by a distance. Okay, so they each move by 2 meters. Okay, so let me back up just 1 second. So they tell you that the speed is 1 meter per second, but let's say this point here, this moves by 2 meters. We can figure out the time. Delta t is the change in x over the velocity, delta x over v. So that's 2 divided by 1, which is 2 seconds. So the time delta t is equal to 2 seconds.